All right. So the last time we have been talking about the interface to the database system. And today we are going to continue talking about that. You're learning a language called SQL, the structured query language. The relevant book chapters are still the ones that I had in my last slides from the Ramakrishnan and Gerke book, the sections 3 and 5. Now, the last time we have seen how you can define the structure of a database in SQL, meaning you can define what are the tables and what are the columns in those tables, and you can define constraints like the primary and foreign key constraints that we have seen last time. And we have also seen how we can insert and delete and update content that you have in those tables. Now, of course, ultimately, once you put data into a database, then at some point you want to actually retrieve it or analyze it in some way. And today we will start discussing about SQL queries, which analyze the content of your database. Now, generally, such an SQL query describes a new relation or a new table to generate. This new table is generated from the content that you have in your database. So this new table that can consist of one single value can also have multiple rows and multiple columns. And in the SQL query, you define what that table should look like and what content you want inside. So very important, we quickly mentioned that in one of the previous lectures, SQL is a declarative language, so you do not instruct the database management system which steps to execute in order to analyze your data. You just describe a desired result and you leave it to the database management system to figure out what is the best way of generating that result. Now, we're going to start with a simple class of SQL queries, which consists of 3 parts, which describe the desired result relation. Now, in the from part of the query, you are specifying the tables from which you want to generate something. So this is essentially the data sources for your analysis. Then in the where condition, you specify certain predicates, certain conditions that the rows in your result relation must satisfy. And in the select part of the query, you specify the columns of the result relation that you want to see. So we are discarding the other columns. All right. The syntax for the simple class of queries is as you see here. In the from clause, you specify the data sources. In the where clause, you specify conditions for row filtering, and in the select clause, you specify the columns that you're interested in. Now, most of that is pretty intuitive. Perhaps the from clause, that one looks a little bit more complicated. So let me say a few words on that. So here in the from clause, we are essentially combining 2 data sources, 2 tables, and we are using the join keyword to do that. So the semantics of what you see here is that I essentially retrieve a pairs of rows containing 1 row from table 1 and 1 row from table 2. And I only want to retrieve those pairs which match, which satisfy a certain condition together. And that condition is specified as the join predicate. So we are only retrieving those tuple pairs, those row pairs, which satisfy together the join condition. Also, you see those little dots on the right-hand side of the from clause. This indicates that you can add more tables. You can join with a 3rd table on some join condition and with a 4th table on some join condition and so on. So you essentially, you can choose how many data sources you want to combine. Of course, if you are dealing with large data sources, then the more data sources you combine, the longer processing could take. Let's make things more concrete by an example query. Now, this example query refers to the database that you see on top, marked in green. It is pretty much the database that we have seen last time. It's a database containing information on students and the courses they're taking. There's one table, one relation for the students with a student ID and a student name. Then there is a table storing the courses with the course ID and the course name. And then there's this enrollment table, which connects the students table to the courses table and essentially stores pairs of a student ID and a course ID with the semantics that the corresponding student is enrolled in the corresponding course. On the lower half of the slide, you see a corresponding query. And perhaps one last thing I should point out about the database, and you might notice that I have underlined some of those columns in those relations. And that typically means that the corresponding columns are primary key. So this is what it means in this case. In some other books on databases, you might find slightly different notations, but this is a typical notation in order to indicate which are the primary key columns. All right. Now, you see this query on the lower part of the slide, and perhaps on the first side, when not being used to it, those queries can sometimes look a little bit complex. So if you want to understand what one of those SQL queries is doing, it's typically good to essentially decompose it and look at the different parts. So if I try to understand what a SQL query is doing, I typically start by looking at the from clause. So let's do that. And if you look at this first part of the from clause, then what we're doing here is we're essentially pairing up students with their enrollment. So we are selecting pairs of one row from the students, representing one student, and we want to retrieve a matching pair in the enrollment relation, which is essentially one tuple with a student ID and a course ID, where the student ID matches the student ID that I have selected in my students table. So this essentially combines each student with the related enrollment information. The second part of this from clause over here combines that with the information in the courses table. So after having matched the students with the enrollment relation only gives me the course ID, but I might also need the course name. So here I'm therefore matching the tuple pairs from the student and the enrollment table that match on the student ID. I'm pairing that with a third tuple from the courses relation, which matches on the course ID. So the result of this entire from clause, those are triples of tuples, one from the students, one from the enrollment, and one from the courses that match on the student ID and on the course ID, because those are the two join conditions you see here. So the next step I'm doing here is that I filter the rows in my result relation using this predicate. And here in this predicate, we are essentially restricting the course name to CS4320. So I want to get, I want to know something about course enrollments for that specific course. All right, so we will discard the rows which don't satisfy this condition in the where clause. Now, finally, we look at the select clause, and here I'm essentially specifying the columns that I want to keep in my result relation. So I will discard those columns which don't appear in the select clause. And as you see throughout this entire query, we have always referred to columns by this notation that you see here. Here I'm selecting the S name, the student name column in the students relation. So if you want to refer to one column of one specific relation, we use the notation relation, aka table name, dot column name. We will also see a couple of alternatives, a couple of simplifications in the following. Now, so now you have seen your first SQL query. In order to get the hang of it, I think it's good to make a little example here. I give you a couple of minutes, maybe 5 is maybe even a little bit much. Here I ask you to find the names of courses in which one specific student named John Smith is enrolled. So give it a try to formulate that SQL query. You can either do it on paper, or you can do it in Postgres if you have it installed, or you can go to this website that I have shown you at the beginning. And here there is one question, whether by doing the select we create a new relation or whether we modify the old one. So in general, this entire SQL query together, all clauses together, is defining one new relation to create. So you cannot say that the select clause alone is creating that relation, but the query in its entirety is essentially creating one temporary result relation that will be shown to the user. All right, so I give you a couple of minutes to make that example, and in the meantime, I'm answering questions that appear in the chat here. Okay, and this is a very good question. Somebody's asking whether we can only join using columns that appear in foreign key constraints. So you might remember from last time, we've seen that we can link the columns from different tables by those foreign key constraints. We essentially specify that values that appear in the columns of one relation must appear as primary key in the columns of in another relation. So you're essentially matching rows from one relation with the foreign key on the columns to rows in another relation. And in those examples here, I have indeed used joins that connect relations which are linked by foreign key constraints. Good observation. Now, in general, this is not necessary. In general, you can formulate arbitrary join conditions and you can formulate arbitrary joins. You can join arbitrary relations. Having said that, the most typical join is actually, so in practice, the most common case is that you join tables with foreign key conditions, but that is not required. All right, and here I'm just accessing the chat. All right, and that is another great question here. Question is whether the order of the tables in the joins matter. Now, the order of the tables does not matter for the query result. Also, internally, the database system might freely choose the order in which it internally executes the operations for joining a table. So it typically does that to optimize the expected running time for answering your queries. So for the final result of the query, the order of your tables in the join does not matter. And if you have a reasonably sophisticated database system, then the order of the tables does not matter for performance either, because the database system internally chooses the order in which it does the joins. We will talk much more about performance later. And left outer joins and right outer joins that as he mentioned here, we will discuss about them later. Yes, so once we come to those left outer joins and right outer joins, which I haven't introduced yet, then the order will matter. But I mean, for the joins that we have discussed so far, the order does not matter. Not for the query result. All right. Okay. And for the solution of the exercise, please currently Don't discuss it in the chat yet. I'm gonna show that to you in a minute. If there's questions left after I quickly go over how to approach this exercise, then please feel free to ask them in the chat. Okay, and here another great question. Now we only selected the students.s name, but in the rest of the query we mentioned many other columns, for instance, in the where condition and so on, in the join conditions. But since we only write the student name column in the select clause, it means that this is the only one that we as users will see afterwards. Okay. All right, I think now we had a couple of minutes and we answered a few questions. So let me actually quickly enter the solution here in Postgres. Quickly share my terminal here. Okay. So I still have the database that we created last time. If I call it university, here you see the names of the tables that we have here. And the goal was to select the names of the courses in which student John Smith is enrolled. So we want to find course names. That's why that's what the column that we finally want to see. And as data sources, we need, of course, the students, because we want to check something about the student name. We need to combine that with enrollment information. And here I'm already using a shortcut that we have not officially introduced yet. So let me write out the name of the students table before the column name. The join condition is that the student ID must match the enrollment student ID. And I'm also combining that with the data source courses. And here we must have that the enrollment course ID matches the courses course ID. Now we want to filter to, oh, and here I have made a little mistake, thank you. And here I want to have the student name match John Smith. So here we are selecting the courses.course name from the students, join with enrollment, join with courses, where the student name matches John Smith. So, right. Okay, and here a little mistake. Now we got it. So here we see that the student is enrolled in two courses, CS 4320 and CS 4321. All right. So, and the order of the join relations for the joins that we are considering right now does not matter. All right. So this is how we can solve this exercise. It is very close to the initial query that we have seen, where we are filtering by the course name and we are retrieving the students. All right. Okay. All right. Yes. And the from clause indeed includes, yes, all the joins. So that is something that you find in the from clause. And the source, meaning the data source, this combines multiple tables. So you cannot answer this query from one single table, since you need, for instance, information about the course name, but also information about the student name, which you don't find in the same table. All right. Now, SQL allows you to write the same SQL query in many different ways. There's many possibilities to reduce writing overheads, and which one you prefer, this might differ from one person to another one. So I'm going to introduce in the following a couple of shortcuts that you may choose to use if you find it easier. Now, one first thing here is that some of those tables in the database, they can have pretty long names, and it quickly gets tedious to write out those names multiple times in the same query. So this is why SQL gives you the opportunity to introduce so-called aliases, which are essentially a shortcut for the names of tables in the from clause. So here you see the same query, but written in two different ways. In the query on the lower half of the slide, we are essentially assigning a shortcut S to the students table here. And then we are using that shortcut in the other parts of the query. For instance, once we are referring to the column that we want to select, and once we are referring to columns in join conditions, right? So this simply saves you typing a little bit when writing the query. And you can even simplify further if column names are unique among the tables that you use in your from clause. So for instance, the student name and the course name columns. The student name column only appears in the students table, and the course name column only appears in the courses table. So if you just write the name of the column, then the database management system should be able to infer the associated table automatically because there's no ambiguity. In those cases, SQL allows you to simply omit the name of the corresponding table. On the other side, if you have something like the student ID or the course ID, the student ID, for instance, appears in the students table, but also in the enrollment table. So if you just write student ID, the database management system does not know which table you are referring to. And that's why for those columns, you have to add the table name or the alias name. All right. And for the alias, both works. You can also use the AS keyword. All right. So this are some shortcuts that you can use in order to simplify the SQL queries that you write. The predicates, for instance, in the where clause that we have seen so far, they have been relatively simple, but SQL supports a very rich set of predicates that you can formulate. Of course, you can use equalities and inequalities. You can, for instance, check if the value in one column is within a list of allowed values. And you can even formulate regular expressions. For instance, here I'm checking whether the course name matches the expression CS followed by some arbitrary sign. Let me quickly move the chat a bit so that I can see more of the slide, and then followed by some arbitrary string. So this percentage sign stands for an arbitrary number of characters, and this underscore stands for one single character. All right, so those are some ways to formulate more diverse predicates, and SQL supports many more types of predicates. But let's say the things that I'm showing you here in my experience, those are perhaps the things that you use most frequently in practice. So if you learn those things, then you should already, you should be able to treat most cases that arise in practice. Of course, you can also compose predicates using the typical operators. You can formulate a logical conjunction by using the AND keyword, or a disjunction by using the OR keyword. You have the not negation, and for instance here, you could check whether the course name is CS 4320 or whether it's 5320. An alternative way of writing that would be by using the in list, the in keyword that we have seen on the previous slide. All right, good. Okay, a couple of questions here in the chat. I think most of them have gotten answered. All right. So beyond the predicates, there's also many more features that you can use in order to write your select clauses. For instance, the tables that you will be working with in practice, often they have a lot of columns, and it can become very tedious to write out all the columns names if you just want to retrieve all the information in a table. So the star operator in a select clause essentially means that you want to retrieve all the columns that you have in your tables, in all the tables that you selected in the from clause. You can make it more specific by writing a table name dot star, and then you retrieve only the columns for one specific table. You can also formulate arbitrarily complex arithmetic expressions in the select clause. You can, for instance, here you can sum up values in 2 columns, and then you can multiply by some constant and so on. That is fine. And especially if you do this, if you use some complex expressions instead of single column names in the select clause, then in order to not get confused by the output of the query, you probably want to introduce some readable name for the corresponding column, and SQL allows you to do that simply by writing the name that you want for the column after here the column name after the AS keyword. So here, for instance, I'm renaming the student name column at the S name column to the more readable student name. I could also use that in order to assign some name to the expression that you see above. There's also a couple of alternative ways of writing those join conditions that we have seen so far. So far, we have been explicitly formulating the join condition, but there is a couple of frequent cases for which people have introduced shortcuts in SQL. For instance, often those join conditions, they are actually equality conditions between columns of different tables. Here, for instance, you can use the using keyword and simply you write the name of the column that should be equivalent, and then it is automatically expanded into this equality condition. Also quite useful in practice is the natural join. A natural join between 2 tables simply means that you want the the values in all columns that have the same name to be equal. So instead of actually typing out the names of all the columns on which you want to match, this one will be expanded automatically. Can be a little bit dangerous because every once in a while, if you're dealing with large tables with many columns, then you know that they have one column of the same name in common, but there might be other columns of the same name that you are not aware of. So the natural join is sometimes a little bit dangerous because every once in a while you will overlook that there is other column pairs than you intend, which also have the same name, and then they get automatically added to the join condition. So table 1 natural join table 2 means I'm retrieving all the pairs of tuples from the first table and the second table, which have the same value in all columns that have the same name. I'm gonna go to show you some examples in a second. Finally, just so you know, you will sometimes find queries where somebody doesn't use the join keyword at all. That is also admissible if you write something from table 1, comma table 2, where join condition, the semantics is basically the same as if you had written table 1 join table 2 on join condition, right? Okay. All right, and now right. Now you should be able to see my screen again. So here, just to show you one example with the natural join. I see that somebody tried it and it gave an error, but I mean, in principle, if you do it like this, it should work. So here we have the students table and the enrollment table. They have one column of the same name. Let me show you this. Right, so the students table has the student ID, and the enrollment table also has the student ID. So if I do the natural join between the two, then that will automatically match them. And you can also do a natural join on multiple tables, as one of you is asking. That's a good question. So here, for instance, if I join with the courses table in addition, then here implicitly I'm adding a match condition for the course ID, which appears in courses, and it also appears in enrollment. Okay, so that is one way of writing this query. And as you see, I'm using the star notation in the select clause in order to retrieve all the columns of the result. Okay. All right, so those are a couple of alternatives about how you can formulate your SQL queries. I encourage you to play with it a little bit and try out different formulations. One last point, so far we have been using the select clause, and if you do this, then in principle, you might get the same row in your result multiple times. Sometimes that's maybe even what you want. Often it's not what you want, and in order to eliminate duplicate result rows, which are kind of boring, you can also use the select distinct notation, and then the database management system will automatically eliminate all the duplicates. Now, so far, we have been generating results that consist of single rows. But if you're dealing with a lot of data, then often you rather want to learn something about aggregates. For instance, you want to count the rows that satisfy certain conditions. And SQL gives you a rich set of aggregates that you can use. Here you see the aggregates that are supported by default. You can count things, you can sum up things, you can average things, you can calculate minima, and you can calculate maxima. Now, we will see a concrete example in a second, just to give you a broad overview of the different aggregates that you can use. You use those aggregation functions typically in the select clause. So instead of getting all the different rows as a result, you would rather get the number of rows, for instance, or the maximum in one specific column. Those aggregates typically have some parameters. For instance, for summing or averaging, you need to indicate which column or which expression you want to sum or average over. One common annotation is if you want to simply count the number of result rows, then you typically use this count and star between parentheses. Sometimes we have already quickly discussed, and we will discuss this in more detail, that SQL allows you to replace unknown values in a certain row, in a certain column, by placeholders, which are called null values. Sometimes you want to count how many result rows you have for which the value in one specific column is known, and you can do this by writing this count, and then as parameter within parentheses you write the name of the column in which you need to have a value. You can also count the number of distinct values that appear in certain columns with the syntax, and this is just some of the most commonly used features. If you're interested and explore a bit, then you would find many more, but this is what you need in most cases, in my experience. This is how we can use that in this example query over here. This is nearly the same query as before, but now I actually don't want to retrieve a specific student names anymore. Now I just want to count how many students are enrolled. So in order to understand what the query does, we can again look at the from clause first, which hasn't changed. So here I'm still pairing up students with enrollment information and combining that with information about courses. Then I'm throwing away all the rows that are not about the CS4320 course. And now, and this has changed compared to before, finally, I simply count the number of remaining rows. And so the result of this query would be one single number, which is the number of people enrolled in CS4320. All right. Let me quickly check whether there's any questions in the chat. Yes. Oh, okay, and this is an interesting question, which already relates to performance. Question is, if we have really large tables, whether it makes a difference for performance, whether we use the count star syntax or the count in one specific column syntax. So the semantics of the two is slightly different. So you might not be able to use both of them interchangeably, but it's a valid question, and it depends a little bit on your database management system. So we will see that in more detail much later in this course. There's database systems which are efficient at retrieving data only from specific columns, and they could potentially benefit from that. There's other database management systems which are not efficient at retrieving data in specific columns separately, but they always retrieve all the information about one row in your table together, so they could benefit less. So it depends a little bit on the type of database system that we are talking about. But that is already a topic that we will discuss later in this course, but great question. All right. Now, here we are aggregating over the entire query result. We are counting all the rows in the result. Often in practice, you actually want to break down things. You want to calculate aggregates for different data subsets. And SQL also allows you a function in order to do that. It's called the group by clause. And there you essentially specify a list of columns that is used in order to partition your data. And then for each partition of your data, for each group, you are calculating, for instance, aggregates separately. So for instance, if I want to know how many students have been enrolled in CS 4320 and how many students have been enrolled in CS 5320, like the second listing of the course, then I could, in this case, issue two separate queries where once I filter to CS 4320 and once I filter to 5320. But it is, of course, more efficient if I can do that just with one single query. And that is the query that you see here. So the beginning is, again, I'm pairing students with enrollments and courses. Then I'm filtering to the rows that either concern 4320 or 5320. And now comes a new aspect, because now I'm partitioning the data based on the value in the course name. So I'm separating the rows for 4320 from the rows for 5320. And finally, I calculate a group-specific row count and display that together with the course name. And I could also leave out the condition in the where clause, and then I would get a breakdown for the enrollment numbers for all courses that are listed in my database. And of course, writing one query like that is much more efficient than to write separate aggregate queries for each specific course. All right. Now, you see here that in the select clause, I'm selecting the count, which is the count of the rows for each group. I'm also selecting the course name. That makes sense because I want to know which group a specific count refers to. But I have to be a little bit careful in general about what I put into the select clause if I am using a group by query, because the result to a group by query must always contain one single row for each group, only one row per group. And that means that in the select clause, I can only ask for columns and aggregates and generate expressions that have one value for each of the groups. For instance, here, for the same course, I could have multiple students enrolled. So for one specific group of results that share the same course name, I might still have different student names. So if I want to add the student name into my select clause, it would mean that I would get multiple result rows for each group, and that is not allowed according to the SQL standard. So here, if I put anything into the select clause which doesn't have one unique value per group, then the database management system will throw an error. Here, I am respecting that because the count is, of course, something which is unique for each group. And the course name is also unique for each group because that is precisely the column that I use in order to define the groups. So by definition, if two rows have different values in the course name column, then it would be in different groups. So within the same group, I only have one specific value in the group by column. All right, and here you see essentially what I just explained, laid out in a little bit more detail. First of all, in terms of evaluation order, as we have seen in this example, grouping is applied after we have filtered by the where clause. And what I also introduced in this example, you have this constraint that the result can only contain one row for each group, and that implies some restrictions on what you can put into the select clause once you're running group by queries. All right, now one last feature that I wanted to mention here. Sometimes in practice, you also want to put some condition on groups as opposed to conditions on single rows. So the where clause is where you put conditions on single rows, and that is evaluated before doing the grouping. Then after the grouping has happened, you might still want to have some condition for filtering out entire groups. You can do that using the having clause. For instance, here in this example, we have added a having clause in order to only show the results for those courses where we have a count of at least 100, which incidentally is the case for those courses here. And then in your query result, you're only shown those groups which satisfy those conditions. So this is it for some first intro to SQL queries. We're going to discuss some more advanced features next time. So I recommend you to revise the material that we have seen today, and also to experiment a little bit. So we have seen different ways in which you can experiment, installing Postgres or using this public website, for instance. You might either create a database yourself using the commands we have seen last time, or you might download some data set from Kaggle, for instance, which matches your interest, and then you load it into a database and experiment a little bit with it. So please explore a little bit with those queries. And if you find out something interesting about the data set, then please feel free to share your insight and the associated SQL query and data set on Piazza, so others might also benefit from that. All right, good. Then have a great day, and see you on Wednesday.